Welcome to NOVA-C.A.E. We are back with another quick ANSYS tutorial. This video tutorial provides a demonstration of simulating bolt behavior during preload and external load. Don't forget to check the description of this video for some useful resource. By the end of this video, you will understand how to set up an axisymmetric finite element model, bolt preload application, contact force extraction and results validation. For demonstration purpose, I am taking example of a bolt and plates assembly. Bottom flange is constrained, and external load is applied on the top flange. To understand the bolt behavior, we will be solving two load cases. In load case 1, bolt preload is applied in the first load step, and external load is applied in the consecutive 3 steps. In load case 2, same setup of the FEA model is used by suppressing the bolt preload. By taking advantage of symmetric behavior of the geometry, loads and boundary condition about the central axis, we can simplify the FEA model to axisymmetric problem. We can extract the induced tensile load on the bolt by extracting contact reactions at the bolt-to-plate interface. Plate crushing load can be extracted from the contact at the plate-to-plate interface. Now we will look into the model setup in ANSYS workbench. I have already imported the CAD model into ANSYS Mechanical. CAD model is generated using ANSYS SpaceClaim. To set up axisymmetric FEA, the CAD model has to be in the positive XY plane. And your axis of symmetry has to be the y-axis. In this case, I have a solid bolt. So the bolt model will be touching the y-axis. Once the model is imported into Mechanical, select axisymmetric from the Details tab. And make sure all the surfaces are imported correctly. You can see that the geometry is in the global XY plane, and the axis of symmetry has to be the y-axis. Now under Connections, in defining the behavior of the touching parts. In this case, I am using a frictionless contact so that the friction losses are neglected, and I will be able to understand just the bolt behavior. Contact tool helps us to identify the contact status of the contacts we just defined. I have generated mesh with default settings, and it just looks fine. To visualize if the axisymmetric is set up properly, I have inserted a symmetry folder. Upon setting the type to 2D axisymmetric, we can visualize the 3D mesh geometry. Lower the value of angle to see a sector view. Once you confirm, set it back to Cartesian. As discussed previously, I am solving the problem in 4 load steps. I applied bolt pretension to the bolt body, and specified the preload value in the first load step. Successive load steps are locked in order to carry forward the preload. Y-directional force is applied on the top flange. Starting from second load step, corresponding load values are entered. Fixity is applied on the bottom flange. After solving the model, plot the maximum principal stress distribution. You can observe that the bolt shank is under tension, and the stress contour makes sense. Plot the contact force reaction at the bolt plate interface. You can observe the variation in load magnitude in the chats below. Make a note of the y-directional force. Similarly plot the force reaction at the plate-plate interface, and note the y-directional force. For ease of understanding, I have plotted the y-directional reaction forces at both the contact interfaces onto a graph. The x-axis indicates the external load. Y-axis indicates reference load. Blue color line indicated the tensile load on the bolt. You can observe that the tensile load on the bolt is constant until the external load matches the bolt preload, beyond which the tensile load on the bolt increases. The red color line indicates the crushing load between the plates. We can observe that, when external load equals 0, crushing load matches with the bolt preload. Upon increase of the external load, the crushing load decreases, until it becomes 0 when the external load matches the bolt preload. For the second load case, I am going to suppress the bolt preload and submit the run. Similar to the first load case, I have extracted the contact reaction forces and plotted on a graph. In the second load case, the black dotted line indicates the bolt tensile load, and the yellow line indicates the crushing load. You can observe that the bolt tensile load increases upon the increase of the external load. It starts from 0 and reaches a value which matches the external load. As there is no preload applied, you can observe that the yellow line indicating the crushing load is 0 with respect to the external load. This graph summarizes the bolt behavior during the preload and external load. In actual practice, the slope of the blue line may change due to bolt play and the stiffness of the plates. This concludes the demonstration of simulating bolt behavior during preload and external load. NOVA-C.A.E is engineering service, an online FEA training firm. We are focused to provide CAE training to students and engineering professionals to enhance the simulation skills, which will help them in better product design abilities and career opportunities. We also provide project assistance. Contact us for more details.